Hello everyone. For the M5 practice hackathon, I worked on the tackle customer churn classification task. The goal is to predict whether a customer will churn so the company can prioritize retention actions. My objective was not only to achieve good predictive performance, but also to build a workflow aligned with responsible AI principle, including fairness, transparency, accountability, and interpretable explanations. The dataset contains information about telecom customers. Each row represents a customer, and the features include service subscriptions, account information such as tenure, contract type, payment method, monthly and total charges, and demographic attributes including gender and senior citizens. The target variable is churn, indicating whether the customer leaves the service. During pre-processing, I focused on data quality and reliability. One issue is that the total charges variables is stored as text and contains blank values. After converting it to numeric, I found 11 missing values, all corresponding to customers with tenure equal to 0. This pattern is consistent with business logic because new customers may not yet have accumulated charges. Therefore, I treated this as valid missing value and handled them using imputation within the pre-processing pipeline. To further support responsible AI reliability, I also applied a lightweight anomaly detection step using isolation forest on key numeric variables such as tenure, monthly charges, and total charges. This helps identify unusual patterns that could potentially distort model training. Next, I built predictive models. I used a 60-20-20 split for training, validation, and test set with stratification to preserve the churn rate across split. I evaluated several models including logistic regression, random forest, gradient boosting, and XGBoost, and also test imbalance handling methods such as SMOD and Edison. Because churn prediction is an imbalance classification problem, I prioritized PRAUC as the main validation metric. The best validation performance came from logistic regression with resembling. On the test set, the model achieved a ROC AUC of about 0.84 and a PRAUC of about 0.63. I also applied stratified key-fold cross-validation to ensure the results are stable and not dependent on a single data split. Another important component of churn modeling is threshold selection. Instead of using the default probability threshold of 0.5, I optimized the threshold on the validation set with a recall constraint. Since missing churners can be consistently for retention strategies, the final threshold of 0.52 achieved around 0.680 recall and an F1 score of about 0.61 on the test set, capturing most potential churners. Next, I evaluated fairness as part of responsible AI. I computed group-based fairness metric. Metrics include demographic, party difference, equal opportunity difference, and equalized odd difference across gender and senior citizen groups. The results show that the model performs similarly across genders with very small differences in error rate. However, fairness gaps are larger for the senior citizen group, indicating that prediction rates and errors differ between senior and non-senior customers. This disparities raises ethical conditions. If charm predictions triggered retention campaigns, fairness gaps could lead to unequal treatment. Even when predicted attributes are not used directly, correlated features such as tenure or contract type can act as a proxies and create unintentional disparities. To address this, I documented the issue and proposed mitigation strategies, including fairness-aware training, threshold governance, and human oversight of sensitive cases. I also emphasize that fairness should be continuously monitored after deployment. To improve interpretability, I applied several explanation techniques. For global explanations, I used SHAP to identify the most important drivers of charm, including tenure, monthly charges, total charges, contract types, and payment method. This result align with business intuition. I also used the PDP and the ICE plot to understand how numeric variables influence charm probability. For example, charm risk generally decreases as tenure increases and tend to rise with higher monthly charges. For local explanation, I used the SHAP waterfall plot to explain individual predictions and apply limb and ankle explanation to avoid additional interpretable insights. Ankle explanation generates role-based conditions that are easier for business stakeholders to understand. I also generate counterfactual explanation use DICE counterfactuals, identify minimal changes that would shift a prediction from charm to retention. Importantly, this suggests the changes focus on controllable business factors such as contract type rather than protected attributes, making them actionable and ethnically appropriate. Finally, I consider production readiness. I create a checklist to cover reproducibility, moderating, data draft detection, fairness monitoring, ad logging, and privacy safeguard. I also save artifacts such as a model comparison, a fairness report, and explanation output to support transparency and accountability. In summary, this project demonstrates a complete responsible AI workflow, strong performance validation, fair analysis across demographic groups, multiple interpretability methods include SHAP and counterfactual explanation, and a product readiness plan to support responsible deployment. Thank you.